Welcome to section 4.4 on L'Hopital's rule. So first we'll go over the statement for L'Hopital's rule and then look at several examples of how to apply it in order to find limits. Okay, so L'Hopital's rule states if the limit as x approaches a for both f of x and g of x is equal to 0, or if the limit as x approaches a for f of x and g of x is equal to either positive or negative infinity, then the limit as x approaches a of the ratio or the quotient of those two functions is equal to the limit as x approaches a of f prime of x over g prime of x. So the limit that we're trying to evaluate is equal to the limit of the derivative of the numerator over the derivative of the denominator. Now this is provided that f and g are both differentiable, their derivatives have to exist on an interval I which contains a, where x is approaching, and that g prime of x does not equal 0. So keep this in mind that in order to be able to use L'Hopital's rule, we need an indeterminate form of the type 0 over 0 or infinity over infinity. Now there are 7 indeterminate forms. In order to use L'Hopital's rule, you need a ratio or a quotient of the type 0 over 0 or infinity over infinity. Now, of the 7 indeterminate forms, if you have one of the other 5, you're going to manipulate it so that you can apply L'Hopital's rule so that you have an indeterminate quotient. Okay, so we're going to work through some examples so you can see how to deal with each of the different types that there are. The first type we're going to consider is where one quantity in your limit is approaching 0 and the other quantity is approaching infinity. So it's the type 0 times infinity. The reason this is an indeterminate form is because one part of your limit is approaching 0, it's shrinking, and then the other part of your terms is going to infinity, it's blowing up. So since they're basically doing opposite things, we cannot determine directly what the limit is. That's why it's indeterminate. So we need to change this to be either of the type 0 over 0 or infinity over infinity. So first example here, the limit as x approaches negative infinity of x squared times e to the x. So we're going to look at each of the parts of this limit separately. If I were to just consider the limit as x approaches negative infinity of the quantity x squared, that would give us positive infinity, right? You could imagine the graph of x squared, or as well just think of substituting in negative infinity, you square it, it becomes positive and it's growing without bound. Now the other part of our terms, e to the x, if I think of the limit as x approaches negative infinity of e to the x, well, think of the graph. Do you remember what e to the x looks like? Our exponential function goes through 0, 1, and it has a horizontal asymptote at y equals 0. So here's e to the x. So as x approaches negative infinity, what is e to the x approaching? That's right, it's approaching 0. So notice here, this limit is of the type infinity times 0. So we have an indeterminate form. The way it's written, I can't apply L'Hopital's rule because it needs to be either 0 over 0 or infinity over infinity. So what I'm going to do is I'm going to rewrite this, and the most easy way to do it is to put that e to the x in the denominator. So I'm going to rewrite this as the limit as x approaches negative infinity of x squared. Now if I move e to the x in the denominator, it's equivalent to e to the negative x being in the denominator, right? And then now let's confirm that we have the correct indeterminate form in order to apply L'Hopital's rule. So if x goes to negative infinity, x squared, my numerator, that's going to approach positive infinity. And then the denominator, so x is going to negative infinity, e to the negative infinity is e to the positive infinity, so now that's approaching infinity. All right, so I can see my limit is now in the form infinity over infinity. Am I allowed to use L'Hopital's rule? Yes, I am. Every time you apply L'Hopital's rule, you need to indicate that that's what you're doing. So you're going to write equals, and then L apostrophe H or LH for L'Hopital to indicate that that's what you're going to do in the next step. So I have the limit as x approaches negative infinity, and now I'm going to take the derivative of the numerator. So the derivative of x squared is 2x, and then the derivative of the denominator separately. You're not doing the quotient rule or anything like that. You're just taking the derivative of the numerator over the derivative of the denominator. So derivative of e to the negative x, using the chain rule, that's going to be negative e to the negative x. All right, so far so good. Now let's check. As x goes to negative infinity, my numerator, 2x, is going to be approaching negative infinity. And the denominator, so I have e to the negative infinity, so e to the infinity. So this part here is approaching infinity, but then I have a minus sign in front of it. So the denominator is approaching negative infinity. So again, I have an indeterminate form of the type infinity over infinity, negative infinity over negative infinity. So I'm going to apply L'Hopital's rule again. And I need to indicate that that's what's going on. So I have the limit as x approaches negative infinity. Now what's the derivative of 2x? It's just 2. And then when I take the derivative of negative e to the negative x, because of the chain rule, I'm going to multiply by another negative. So now it's going to become positive e to the negative x. All right, so far so good. So now let's check. As x approaches negative infinity, well, the numerator is a constant, so it's just approaching 2. And then the denominator, e to the negative infinity, that's going to be approaching positive infinity. So when I have a constant over infinity, that means the entire quantity is approaching 0, right? The denominator is blowing up and the numerator is not changing, so the entire expression is shrinking. So we figured out that the limit is equal to 0. Nice job. So that took 2 iterations of L'Hopital's rule, and that can happen on occasion. So just stick with it, but just pay attention to if your limit, your ratio is getting simpler or if it's getting a little crazier. That way you know whether or not you should proceed. All right, let's look at other indeterminate types. So we have here the type infinity minus infinity. So why is this an indeterminate form? Well, first let's look at some other cases. If you had a limit of the type infinity plus infinity, well, that would just result in positive infinity. Both terms are heading in the same direction towards positive infinity, so everything's getting larger and larger in positive direction. If you had negative infinity minus infinity, again, that limit would result in negative infinity because both quantities are getting larger and larger, but in the negative direction. The problem with infinity minus infinity is that both terms are not heading in the same direction. One part of your limit is going towards positive infinity, is getting infinitely larger, and the other part is going towards negative infinity. And something you may study later on in your math courses is that not all infinities are of the same size. So we basically don't know if it's positive infinity or negative infinity that's going to be controlling the limit or the situation, or perhaps they're growing at a similar rate. So what you do is you need to change this to an indeterminate form of the type 0 over 0 or infinity over infinity so that we can use L'Hopital's rule. And you can do this typically one of 3 ways. One is you can get a common denominator with your 2 terms. The second is you could rationalize the expression, either the denominator or the numerator. And the last one is by factoring. So let's look at an example here. We have the limit as x approaches 0 from the right of cosecant x minus cotangent of x. So let's first analyze what's going on. So as x approaches 0 from the right, what is cosecant of x approaching? Well, do you remember your graph for cosecant? Remember, it's the reciprocal function of sine. So everywhere that sine is equal to 0, cosecant has a vertical asymptote. So that would be at 0, as well as at pi, and negative pi, so on and so forth. This is pi over 2, negative pi over 2. Here's 1, here's negative 1. So we've got vertical asymptotes here for cosecant. And then they have in common the value pi over 2 comma 1. And remember, the graph of cosecant goes away from the x-axis. And then here's the other half. I've just sketched one period for you. So this is y equals cosecant of x. So what is the limit as x approaches 0 from the right? So as we approach 0 through positive values, we see that the graph is approaching positive infinity. So this term is going towards infinity. Well, what about cotangent of x? So let's graph cotangent. Do you remember what cotangent looks like? Very similar to tangent, but its asymptotes are at 0 and pi. The period is just pi. And then remember, it crosses the x-axis at pi over 2. And it looks a little bit like x cubed, except it's decreasing, right? And it's bounded between those two asymptotes. So here's one period of y equals cotangent of x. If we want to draw another period, we can. There's negative pi over 2, negative pi. We have another vertical asymptote here. And let's just draw one more period to help us out. All right, wonderful. Now again, we're going to look at the limit as x approaches 0 from the right-hand side. And we see that the graph is approaching positive infinity. So we have an indeterminate form of the type infinity minus infinity. So let's see if we can rewrite it somehow. I'm going to go with the first option, that of getting a common denominator, since I can easily rewrite cosecant and cotangent in terms of sine and cosine. So I have the limit as x approaches 0 from the right of 1 over sine x minus cosine x over sine x. Oh, well, that worked out. They already have a common denominator. So I don't really have much else to do besides rewrite them over that same denominator, sine x. And so I have 1 minus cosine x over sine x. All right, now let's evaluate our limit. So as x approaches 0 from the right, I'm going to have 1 minus cosine of 0 is 1. So this is approaching 1 minus 1, which is 0. And the denominator, sine of 0, that's also approaching 0. So here I have an indeterminate form of the type 0 over 0, which means I am allowed to use L'Hopital's rule. So let's indicate that we're doing that. And then I have the limit as x approaches 0 from the right. Now derivative of the numerator, so derivative of 1 is 0. Derivative of negative cosine x is going to be a positive sine x. And then let's take the derivative of the denominator. Derivative of sine x is just cosine x. So can we evaluate our limit here? Let's see. So as x approaches 0 from the right, sine of 0, well, that's approaching 0. And cosine of 0 is approaching 1. So we're basically done now. The numerator is going to be 0 over 1, which is just 0. All right, nice job. Let's look at some more indeterminate types. We have 0 to the 0, infinity to the 0, or 1 to the infinity. So in this case, your base, you have some sort of exponential expression going on. Either the base is approaching 0 and the exponent's approaching 0, the base is approaching infinity and the exponent's approaching 0, or the base is approaching 1 and the exponent's approaching infinity. So these are our 3 remaining indeterminate forms. Well, again, we needed to change it to the type 0 over 0 or infinity over infinity. How do we do that? Well, we take the natural log of the function, use our logarithmic properties to rewrite and bring that exponent down in the front. Or you could rewrite it as an exponential. So to save you a little bit of time for what that means at the end, because we're going to take the natural log of the original quantity we're trying to evaluate its limit, what happens when we do this? Well, say you have some function f of x and you want to know its limit. Well, if we take the natural log of that function and we get the result that its limit is k, some constant, then the following is true. The limit as x approaches a of f of x is equal to the limit as x approaches a of e to the natural log of f of x, right? If I take e and raise it to the natural log of some function, I just get back f of x. And then since e is continuous, I'm allowed to pass that limit through to the exponent and leave the base as is. And if we've established that the limit of the natural log of f of x as x approaches a is k, then I can substitute that result for the exponent, which means our final result for the limit as x approaches a of f of x is going to be e to the k. All right, so after you take the natural log of the function and you evaluate its limit and you get some constant, the final answer to the original problem is e raised to whatever you got for that limit. Okay, so here's an example. We're going to find the limit as x approaches infinity of e to the x plus x raised to the 1 over x. So let's investigate what's going on right now. As x approaches infinity, well, e to the x is going to infinity. X is also going to infinity. So the base here is approaching infinity. Now let's look at the exponent, 1 over x. As x approaches infinity, 1 over x approaches 0. So notice I have an indeterminate form of the type infinity raised to the 0. So what am I going to do? Well, I'm going to find the limit of the natural log of the function. Okay, so I'm going to consider the limit as x approaches infinity of the natural log of e to the x plus x raised to the 1 over x. Now, the nice thing about logarithms is I have all these wonderful properties I can use. So I can take that exponent 1 over x and bring it down in the front, right? Multiply by it. And so we're going to have here now the limit as x approaches infinity of 1 over x times the natural log of e to the x plus x. All right, now remember, my goal is to try to be able to use L'Hopital's rule. So I need an indeterminate quotient. I need 0 over 0 or infinity over infinity. And this little x, he's just asking to be put in the denominator, isn't he? So I'm going to rewrite this as the limit as x goes to infinity of the natural log of e to the x plus x over x. Now let's see. Am I allowed to use L'Hopital's rule from here? Okay, so if x is going to infinity, well, we've already established e to the x plus x, that's going to infinity. You remember what the graph of ln looks like? I hope so. So here's the graph of ln. We've got a vertical asymptote. It goes through 1, 0. So if x, or the input, is approaching infinity, then ln is also approaching infinity. And then as x approaches infinity, clearly x in the denominator is also going to infinity. So we have an indeterminate form of the type infinity over infinity, which means we're allowed to use L'Hopital's rule. Great. So I'm going to indicate that that's what I'm doing. And then I'm going to write the limit as x approaches infinity. Now, the derivative of natural log of e to the x plus x, it's always 1 over whatever the quantity is there. So e to the x plus x. And then by the chain rule, I need to multiply by the derivative of e to the x plus x. Well, derivative of e to the x is just going to be e to the x, and the derivative of x is 1. All right, the numerator is done. Now I need to take the derivative of the denominator. Well, the derivative of x is just 1. So we're done. Now things are looking a little messy, so let's rewrite this. I have the limit as x approaches infinity. I'll put e to the x plus 1 over e to the x plus x, and I don't have to put over 1 anymore. And let's see if we can evaluate the limit. So as x approaches infinity, e to the x, that's approaching infinity, plus 1, still going to infinity. And then the denominator, e to the x plus x, that's also approaching infinity. So I still have an indeterminate form of the type infinity over infinity. But I'm allowed to use L'Hopital's rule with this form. So here we go, one more time. So now I have the limit as x approaches infinity. Derivative of the numerator, derivative of e to the x is just e to the x. Derivative of 1, 0. What about derivative of the denominator? Derivative of e to the x is e to the x. Derivative of x is 1. Great. Let's see here now. So as x approaches infinity, the numerator, e to the x, that's approaching infinity. Denominator, same thing. Infinity over infinity, that's an indeterminate form. L'Hopital's rule, yet again. So we have the limit as x approaches infinity. Now, before you just keep going 10 times through, you want to look at what you're working with your limit and say, is it getting simpler, or are these derivatives making it kind of get messier, and is it spiraling out of control? And I definitely can see that things are cleaning up with each iteration of L'Hopital's rule, so I know I'm on the right track. All right, but check, because sometimes if you apply it too early or incorrectly, your quantity will get really messy and ugly, and it's time to rethink your strategy. Okay, derivative of the numerator, e to the x, that's just e to the x. Derivative of e to the x plus 1, it's going to be e to the x plus 0, so e to the x. Well, e to the x over e to the x, that's just 1. So this is the limit as x approaches infinity of 1, and the limit of a constant is always itself. All right, awesome. Are we done? Should we box it? No, remember, this is the derivative of the natural log of our original quantity, our original function. So this means the answer, or the result for the limit as x approaches infinity of e to the x plus x, the original to the 1 over x, is equal to e raised to whatever we got for our limit for the natural log of that function, which is equal to e. And you must write out this last step in order to receive full credit or have a correct answer. You need to rewrite the original function and then state the limit of that equals e to whatever you got. Okay? Very nice. How about one more? So we have the limit as x approaches 1 of 1 minus x plus natural log of x over 1 plus cosine of 9 pi x. So always start out, just investigate, see where things are going with the way your function is originally written. So x goes to 1. In the numerator, I'm going to have 1 minus 1 plus ln of 1. So that means the numerator is approaching 0. Denominator, I'm going to have 1 plus, well, this is an odd multiple of pi, so cosine is going to be negative 1. So this is going to be also approaching 0. So I have an indeterminate form of the type 0 over 0, which means I'm ready to use L'Hopital's rule right away. So we have the limit as x approaches 1. Now let's see. Let's take the derivative of the numerator. So derivative of 1, 0. Derivative of negative x, negative 1. Plus derivative of natural log of x, 1 over x. Over derivative of 1, 0. Derivative of cosine of some quantity is negative sine of that quantity times derivative of the argument, which is going to be 9 pi. All right, looks good. Can I evaluate the limit the way it's written right now? Well, let's see here. So the numerator, as x approaches 1, I'm going to have negative 1 plus 1, so the numerator is approaching 0. And then as x approaches 1, well, sine of odd multiples of pi, that's going to be 0. And then 0 times 9 pi, that's still going to 0. So 0 over 0 is an indeterminate form, but I'm allowed to use L'Hopital's rule yet again. So I have the limit as x approaches 1. All right, derivative of the numerator. Derivative of negative 1 is 0. Derivative of 1 over x, that's x to the negative first, so it's going to be negative 1 over x squared. All right, now let's look at the denominator. So I have derivative of negative sine of some quantity. So that's going to be negative cosine of that same quantity, 9 pi x. And then by the chain rule, I have to multiply by another 9 pi. So I'm going to have 9 pi times 9 pi, or 81 pi squared, hanging out down there. All right, can I evaluate the limit now? Well, let's see here. These two negatives are going to cancel out. The numerator is going to approach positive 1. And then the denominator, remember, cosine of odd multiples of pi is going to be negative 1 times that 81 pi squared. That's just a constant. So it looks like we have some sort of finite number. We're done. That's our limit. So it's negative, always put the negative in the numerator, 1 over 81 pi squared. Ooh, that's a squared. All right, we can box it with pride. That was a job well done. So that concludes the section on L'Hopital's rule. Be sure to comment, like, and subscribe, and stay tuned for the next video.